Look up at the night sky, and it feels crowded with stars, but that feeling is an illusion. More than 99.9999% of the universe contains almost nothing. Not stars, not galaxies, just emptiness. And right now, that emptiness is expanding faster than light itself. This isn't a malfunction, it's the plan. What you call reality, stars, galaxies, your existence, isn't normal. It's a temporary exception. And once you understand why the universe chose emptiness, you'll see why this moment exists at all, and why it was never meant to last. Stay until the end. The reason is more unsettling than destruction. Before we begin, if you find value in these deep space videos, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. There is a measurement that astronomers don't talk about much in public, not because it's uncertain, not because it's debated, but because once you hear it, you can't stop thinking about it. It changes the way you see photographs of galaxies, the way you imagine the night sky, the way you understand the word universe itself. The measurement is simple, precise, disturbing. Most of reality is nothing, not nothing in the poetic sense, not nothing as metaphor or mystical absence, nothing as a physical, measurable, mappable property of the cosmos, nothing you can quantify, nothing you can see in data, nothing that has been surveyed, documented and confirmed by every major astronomical institution on Earth. When we look out into the universe, we see galaxies, spirals of light, clusters of stars, nebulae glowing against darkness. Our telescopes capture these structures in exquisite detail. The Hubble Space Telescope, the James Webb Space Telescope, observatories scattered across mountains and deserts. We build catalogues, we name things, we fill our images with light. But the images lie, not because they're false, because they're incomplete. Every photograph of deep space is a selected view, a spotlight aimed at the rare exceptions in an ocean of absence. We point our instruments toward galaxies because galaxies are what we want to study. We frame our images around matter because matter is interesting. We crop out the nothing, and there is so much nothing. Picture this. Imagine standing in the middle of an enormous stadium, a space so large it takes 15 minutes to walk from one end to the other. Now imagine that in this entire stadium there are only 3 grains of sand, not 3 handfuls, 3 individual grains, one near the entrance, one at the 50-yard line, one tucked in a corner beneath the seats. That's not quite accurate. The stadium isn't big enough. When astronomers say the universe is empty, they're not speaking philosophically. They mean it the way an engineer means a tank is empty, or a chemist means a vacuum chamber is empty. They're describing particle density, the number of atoms occupying a given volume of space. It's one of the most fundamental measurements we can make. Count the particles, measure the volume, divide. In your lungs right now, in the air you're breathing, there are roughly 25 septillion molecules per cubic meter. That's 25 followed by 24 zeros. Dense enough that sound waves can travel. Dense enough that you can feel wind. Dense enough to sustain fire, carry scent, transmit pressure. At sea level, Earth's atmosphere has weight, presence, substance. Now, leave the planet. Travel beyond the moon, past Mars, out beyond the orbit of Neptune where sunlight grows faint and cold. You're in interplanetary space now, the region between worlds, where spacecraft drift and comets pass. It feels empty. It looks empty. Your intuition says there's nothing here. You'd be wrong. Even in interplanetary space, there are still about 5 particles per cubic centimeter. Mostly hydrogen atoms, electrons, ions flung outward by the solar wind. Sparse compared to Earth's atmosphere, yes, trillions of times thinner, but not truly empty. Not yet. Keep going. Travel beyond the edge of the solar system, past the heliopause where the sun's influence ends and the interstellar medium begins. Now you're in the space between stars, the vast darkness separating our sun from Alpha Centauri, from Sirius, from the thousands of points of light visible on a clear night. Here, the density drops to roughly 1 atom per cubic centimetre. 1. If you could hold out your hand in interstellar space and close your fist around a cubic centimetre of volume, about the size of a sugar cube, you might capture a single hydrogen atom. Maybe, maybe not. Probably you'd catch nothing at all. And interstellar space is crowded compared to what comes next, because most of space isn't interstellar. Most of space is intergalactic. The Milky Way galaxy, our home, our island of stars, the bright band arcing across summer skies, contains somewhere between 200 billion and 400 billion stars. An unimaginable number. If you started counting them right now, 1 per second, without pausing to sleep or eat, you'd still be counting for 6 to 13,000 years from now. The Milky Way is enormous, roughly 100,000 light years across, so vast that light, travelling at 300,000 kilometers per second, about 186,000 miles per second, fast enough to circle Earth 7.5 times in a single second, takes 100,000 years to cross from one edge to the other. If a Neanderthal standing in a cave in Europe had pointed a beam of light toward the other edge of the galaxy 100,000 years ago, that light would have travelled through the rise and fall of every civilization in history and would only just be reaching the far rim right now. And yet, the Milky Way occupies only a tiny fraction of the observable universe. The observable universe, the spherical region of space from which light has had time to reach us since the Big Bang, extends roughly 46.5 billion light-years in every direction. That's not a typo. 46.5 billion. The universe has been expanding while that light travelled, stretching the distances, pushing the boundaries outward. The total volume is staggering, 93 billion light-years across, 4 times 10 to the power of 80 cubic meters. How many galaxies fill this volume? Astronomers estimate somewhere around 2 trillion, 2 million galaxies, each containing billions or trillions of stars, scattered across the observable cosmos like cities across a continent. The Sloan Digital Sky Survey mapped over 1 million of them. The Hubble Space Telescope's deep field images revealed thousands in a patch of sky, smaller than a grain of sand held at arm's length. 2 trillion galaxies sounds like abundance. It sounds like the universe is full, except galaxies aren't touching. They're not packed side by side like books on a shelf. Between galaxies lies intergalactic space, regions so empty, so profoundly devoid of matter, that the density drops to roughly the equivalent of 1 hydrogen atom per cubic meter. Not per cubic centimetre, per cubic meter. A volume the size of a washing machine, the size of a small closet, might contain a single atom. 1 particle of hydrogen drifting alone in the dark. And even that's an average. In the largest voids, the supervoids mapped by galaxy surveys, the density can drop even lower. 1 atom per 10 cubic meters. 1 atom per 100. Let that sit for a moment. Here's what it means in human terms. If you shrank the sun down to the size of a white blood cell, an object about 10 microns across, invisible to the naked eye, and you placed it in the middle of a football field, the nearest star on this scale would be somewhere in the next city over, miles away, and between them, crossing highways and neighbourhoods and parks, there would be almost nothing. A hydrogen atom here, another one there, scattered so thinly you could walk for hours without encountering a single particle. That's the space between stars. Now zoom out further. If the Milky Way were the size of a coin, a quarter lying on a table, the nearest major galaxy, Andromeda, would be another coin about an arm's length away. Between them, in that empty space, in all those cubic meters of void, the average density is 1 atom per cubic meter. 1 atom in a box the size of a washing machine. And most of the universe isn't even that dense. Most of the universe is the space between galaxy groups, between galaxy clusters, between the giant walls and filaments of the cosmic web. Out there, in the supervoids, the density can drop to nearly zero. Regions millions of light years across where you could travel for eons and never encounter a single particle of matter. How much of the observable universe is this empty? The data from the Planck satellite, from the Sloan Digital Sky Survey, from decades of painstaking measurement gives us an answer. Galaxies occupy less than 0.0001% of the observable universe by volume, less than 1/1,000,000th. If you added up every star, every planet, every gas cloud, every particle of dust in every galaxy across the entire observable cosmos and calculated the total volume they actually occupy, it would be a rounding error, a speck, a vanishing fraction. The rest is emptiness. This isn't speculation. You can see it, not with your eyes. Human vision evolved to detect predators and fruit, not cosmic structure. But you can see it in the data, in the three-dimensional maps built by galaxy surveys over the past 30 years. The Sloan Digital Sky Survey, operating from Apache Point Observatory in New Mexico, spent over a decade mapping the positions of millions of galaxies. They measured their distances, their velocities, their locations in three-dimensional space. When they assembled the data into a single map, the structure was undeniable. Galaxies cluster along thin filaments and broad walls, like foam on the surface of the ocean. Between them lie voids, vast empty regions, roughly spherical, some stretching 100 million light-years across. The Boötes void, the Eridanus supervoid, the KBC void, which may contain our own local group. These voids aren't gaps between objects, they're the dominant features. Imagine mapping every building in a country, then realizing that 99% of the country is wilderness. The buildings aren't scattered across empty land. The land is the thing, and the buildings are rare exceptions clustered in a few places. That's the universe. Emptiness isn't the background. Emptiness is the substance. Matter is the exception. The cosmic microwave background, the afterglow of the Big Bang, mapped in exquisite detail by the Planck satellite and the Wilkinson microwave anisotropy probe, confirms this. When physicists calculate the total energy density of the universe, they find that ordinary matter, the atoms that make up stars, planets, gas clouds, everything we can see and touch, accounts for less than 5% of the total. 5%. The rest is dark matter, dark energy, and empty space. But even that 5% isn't spread evenly. It clumps, it clusters, it gathers into galaxies separated by voids so large they defy comprehension. Robert Kirshner, an astronomer at Harvard, spent years studying these voids. He described them as not the space between things, but the thing itself. The voids are real structures. They have shapes, boundaries, properties. They grow over time. They evolve. And they're expanding. So here we are. We live on a planet orbiting a star, in a galaxy containing billions of other stars, floating in a universe that is almost entirely empty. The matter we're made of, the atoms that form our bodies, our world, the light we see in the night sky, all of it occupies less than 1/1,000,000th of the volume of the observable cosmos. We are the rare exception in an ocean of absence. But knowing the universe is empty doesn't answer the real question. Why? Why is the universe structured this way? Why do galaxies trace filaments and walls instead of filling space evenly? Why does matter cluster in some places and abandon others? Why is emptiness the rule and substance the exception? The answer isn't random, it's not an accident. The architecture of emptiness follows laws, patterns, rules written into the fabric of reality from the first moments after the Big Bang. And those rules, those forces that carved out the void and gathered matter into islands of light, are stranger than you think. Because emptiness isn't passive, it's not what's left over when you remove the matter. Emptiness has structure, and that structure tells a story that begins 13.8 billion years ago, in a moment so violent and so brief that it almost defies description. A story that explains why the universe looks the way it does, and why it will never look this way again. For most of human history, we thought galaxies were scattered randomly across space, like stars scattered across the night sky, like sand grains blown across a beach, distributed evenly, or close enough to evenly that the differences didn't matter. No pattern, no organization, just vast numbers of galaxies filling the cosmos in every direction, each one positioned by chance. It made sense. Why would the universe have a pattern? Why would emptiness have shape? Structure implies design, intention, some guiding force arranging things deliberately. The universe doesn't work that way. Physics operates on simple rules applied locally. Gravity pulls, particles collide, energy disperses. Order emerges from chaos on small scales. Sure, crystals form, planets orbit, stars ignite. But on the largest scales, across billions of light years, we expected randomness. We were wrong. The universe has architecture. Galaxies aren't scattered. They're arranged. Not by design, not by intention, but by forces so fundamental, so deeply woven into the fabric of reality, that they create patterns visible across the entire observable cosmos. And the pattern is disturbing, because when you map where galaxies actually are, when you plot their positions in three-dimensional space and step back to see the full picture, you discover something impossible to ignore. The emptiness isn't random. Emptiness has structure. In the early 1980s, astronomers began a project that would take decades to complete. They wanted to map the universe, not just catalogue galaxies. Thousands of catalogues already existed, listing positions and brightnesses like census data. They wanted to know where galaxies actually were in three-dimensional space, their distances, their relationships, the true architecture of the cosmos. The first major survey was called the CFA Redshift Survey, conducted by the Harvard-Smithsonian Center for Astrophysics. Margaret Geller and John Huckra led the effort. They measured the redshift of galaxy light, the stretching of wavelengths caused by cosmic expansion, and used it to calculate distance. Simple in principle, grueling in practice. Each measurement required hours of telescope time. Each galaxy had to be identified, tracked, measured, verified. By 1986, they had mapped roughly 1,000 galaxies in a thin slice of sky. When Geller plotted the results, she saw something no one expected: a pattern. Galaxies weren't distributed evenly. They clustered along thin filaments and broad sheets like a vast cosmic web. Between these structures lay enormous voids, regions hundreds of millions of light years across containing almost no galaxies at all. The discovery was published in the Astrophysical Journal. The scientific community reacted with skepticism at first. Maybe it was a fluke. Maybe the survey sample was too small, the data incomplete. Maybe they were seeing patterns that didn't exist, the way your brain finds faces in clouds. But then other surveys confirmed it. The 2-degree field Galaxy Redshift Survey in Australia, the Sloan Digital Sky Survey in New Mexico, which would eventually map over 1 million galaxies, the 6-degree field Galaxy Survey, each one using different telescopes, different methods, different regions of sky, found the same thing, the same structure, the same impossible pattern. Galaxies trace filaments stretching across hundreds of millions of light years. Where filaments intersect, galaxies gather in dense clusters, the Virgo cluster, the Coma cluster, enormous congregations of thousands of galaxies bound together by gravity. The filaments connect these clusters like bridges, like highways in a network spanning the cosmos. Between the filaments lie voids, Not gaps, not spaces between objects, voids. The Boötes void, discovered in 1981, stretches roughly 330 million light-years across. It would take 330 million years to cross. When that journey began, the Earth didn't even have 7 continents. All the land was still smashed together into the supercontinent Pangaea. While that light travelled through the dark, the entire face of our planet broke apart and drifted into the world we recognise today. The void is so large that Earth's entire modern history fits inside a single trip across it. The Eridanus supervoid, the Sculptor void, the Capricornus void, each one enormous, each one nearly empty. And here's what makes this unsettling. When you add up the volume occupied by filaments, walls, and galaxy clusters, all the regions where matter actually exists, it accounts for less than 10% of the total volume surveyed. Less than 10%. The voids occupy more than 90%. Emptiness isn't the background. Emptiness is the dominant feature, the substance, the thing the universe is mostly made of. And it has shape. Picture this. Take a sponge, the kind you use to wash dishes full, of holes and tunnels and connected cavities. Hold it up to the light, you see structure. The solid material forms thin walls and filaments surrounding empty spaces. The holes aren't random, they're connected. They flow into each other. The sponge is mostly air, but the small amount of solid material defines the shape. Now imagine that sponge stretched across billions of light years. That's the universe. Galaxies trace the solid parts, the thin walls, the narrow filaments. Voids occupy the holes. And just like in a sponge, the voids aren't isolated. They connect, they touch, they form a network of absence that extends throughout the observable cosmos. Astronomers call this the cosmic web. It's not a metaphor, it's a description. When you map millions of galaxies and plot their positions in 3-dimensional space, the structure looks like a web. Filaments branch and merge, walls spread across vast regions. Nodes mark where filaments intersect, creating dense clusters of galaxies. The Sloan Digital Sky Survey's 3-dimensional map shows this clearly. You can see it, thin threads of galaxies stretching across the darkness, broad sheets tilted at angles, and everywhere between the light, the voids. But here's the paradox. Galaxies don't trace the mass of the universe. Most of the mass, about 85% of it, is dark matter. Invisible, undetectable, except through its gravitational effects. It doesn't emit light, it doesn't absorb light, it doesn't interact with ordinary matter except through gravity. And yet, galaxies trace dark matter's structure perfectly. How do we know? Because the pattern is too precise to be accidental. Galaxies cluster along filaments because dark matter clustered there first. Dark matter forms the scaffolding, the invisible framework, and galaxies simply mark where that scaffolding exists, like lights strung along the support beams of a bridge. The lights aren't the structure, they reveal it. Computer simulations confirm this. When physicists model the universe using only gravity, dark matter, and the initial conditions from the Big Bang, the simulations produce cosmic webs identical to what we observe. The filaments, the walls, the voids, all of it emerges naturally from the mathematics of gravitational collapse. But this creates a deeper question. If galaxies trace invisible scaffolding, if 90% of the volume is voids, if matter occupies only the thinnest structures in the cosmic web, then what does that make the voids? Are they truly empty? The answer depends on how you define empty. If you mean devoid of galaxies, then yes, voids are empty. The Boötes void contains only about 60 galaxies across its entire 330 million light-year span. For comparison, a region of similar size filled with the cosmic average density would contain roughly 2,000 galaxies. 60 versus 2,000. The void contains 3% of the expected number. 3%. But Voids aren't vacuums. They're not regions where matter was removed or destroyed. They contain gas, thin, diffuse hydrogen spread across unimaginable distances. They contain dark matter, though far less than in filaments or clusters. They contain radiation, photons from the cosmic microwave background passing through unimpeded, and they're expanding. This is what surveys revealed that was truly strange. Voids grow over time. They're not static, not frozen in place. As the universe expands, as space itself stretches, voids expand faster than the regions around them. The emptier a region is, the faster it grows. Regions with less matter have weaker gravity, which means expansion encounters less resistance. It's a feedback loop. Empty regions expand. Expansion makes them emptier. Emptier regions expand even faster. Meanwhile, the filaments and clusters contract. Gravity pulls matter together. Galaxies fall toward each other along filaments. Clusters grow denser. The cosmic web sharpens. Filaments becoming thinner, voids becoming larger, the contrast between matter and emptiness increasing with every passing million years. What we see today is a snapshot, a single moment in an ongoing process. The universe is sorting itself. Matter gathering in some places, emptiness expanding in others. And here's what that means in human terms. Imagine watching a city over thousands of years as people slowly abandon the outskirts and gather in the center. Buildings empty. Streets go dark. The inhabited core grows brighter, more crowded, more connected, while the outer regions become silent, not destroyed, not erased, just empty. That's happening to the universe. On the largest scales, matter is retreating into filaments and clusters, while voids expand into the space left behind. The architecture is sharpening. The pattern is becoming more extreme. The universe is becoming more empty over time. Not less. More. So we know the universe has structure. We know galaxies trace filaments, that voids dominate the volume, that emptiness has shape and grows over time. The cosmic web is real, measured, mapped, confirmed by every major survey conducted over the past 40 years. But knowing the structure exists doesn't explain how it formed. Why do galaxies cluster in filaments instead of spreading evenly? Why do voids occupy 90% of space? Why does the universe look like a sponge, like a web, like foam on the surface of an infinite ocean? The answer isn't written in the present, it's written in the past. In the first moments after the Big Bang, when the universe was unimaginably hot and dense, small variations in density appeared. Tiny fluctuations, regions slightly denser than average, regions slightly less dense, differences so small they were almost negligible, variations of 1 part in 100,000. Almost nothing, but those variations were enough, because gravity is patient, gravity is relentless, and gravity amplifies differences instead of smoothing them out. Dense regions attracted more matter. Less dense regions lost matter. The small became large, the large became enormous, and emptiness began forming almost immediately, not from destruction, not from removal, but from segregation, from the fundamental tendency of gravity to gather matter in some places and abandon it in others. The voids we see today were born in those first moments. The filaments, the walls, the cosmic web, all of it traces back to fluctuations so small, so subtle, that they should have been insignificant, except they weren't, because the universe had time, billions of years for gravity to work, billions of years for small differences to become chasms, billions of years for emptiness to carve itself into the structure of reality. And the process isn't finished. It was 1964, and 2 physicists at Bell Labs in New Jersey were trying to eliminate noise from a radio antenna. Arno Penzias and Robert Wilson weren't searching for cosmic secrets. They were engineers troubleshooting equipment, a large horn-shaped receiver designed for satellite communications, but no matter what they did, no matter how carefully they calibrated, cleaned, even removed pigeon droppings from inside the antenna, a faint hiss persisted in their data. A signal, uniform, constant, coming from every direction in the sky. They couldn't explain it, they couldn't eliminate it, and they had no idea they were listening to the echo of creation itself. The signal was the cosmic microwave background, radiation left over from the Big Bang, stretched and cooled over 13.8 billion years of cosmic expansion. Light from a time before stars, before galaxies, before atoms even existed. The oldest light in the universe reaching across time to tell us something fundamental about how reality began. And what it told us was disturbing, because when astronomers finally mapped that radiation in detail, using satellites like COBE in the early 90s and later WMAP and the Planck Observatory, they discovered something impossible to reconcile with our intuition about how things should work. The early universe wasn't smooth, not perfectly, not quite. There were variations, tiny differences in temperature, in density, scattered across the infant cosmos like ripples on the surface of an otherwise calm ocean, 1 part in 100,000. That's how small the differences were. Regions slightly hotter, regions slightly cooler. Fluctuations so subtle they should have been meaningless. Except they weren't meaningless. They were the seeds of everything. The galaxies, the voids, the cosmic web. Every structure we see today, every island of matter surrounded by oceans of emptiness, traces back to those tiny imperfections in the moments after the Big Bang. But here's the part that changes everything. Those imperfections should have disappeared. Go back to the beginning, not to the Big Bang itself. That moment is too extreme, too compressed, beyond the reach of our current physics. But to the universe as it existed, roughly 380,000 years after the Big Bang. This is the moment captured in the cosmic microwave background, the moment when the universe cooled enough for atoms to form, for light to travel freely through space for the first time. The temperature at this moment was roughly 3,000 degrees Kelvin, hot enough to melt rock, but cool compared to the plasma inferno that preceded it. The density was enormous by modern standards. Matter filled space far more evenly than it does today. Not perfectly uniform, those 1 part in 100,000 variations existed, but close. Imagine this. If you could take a cubic meter of space from that early universe, it would contain roughly 1 billion particles, 1 billion hydrogen nuclei, electrons, photons, all churning in a hot, dense soup. Now take another cubic meter from a different location, millions of light years away. It would contain essentially the same number of particles. Maybe 1,000,000,001, maybe 1,000,000,000 minus 1. The difference would be negligible, 1 part in 100,000, a rounding error. And here's what should have happened. Those tiny differences should have averaged out, smoothed, disappeared. Because that's what systems do. Heat spreads from hot regions to cold ones. Particles flow from high-density areas to low-density areas. Turbulence mixes, diffusion equalizes. Given enough time, given the constant churning motion of particles in the early universe, you'd expect uniformity. Perfect uniformity. A universe where matter spread evenly across all of space, where every cubic meter contained the same density, where galaxies never formed because there was nothing to trigger their formation. No clumps, no seeds, no variations to amplify. A universe of perfect emptiness, or perfect fullness. Either way, featureless, dead, dark. That's not what happened. The cosmic microwave background shows us exactly what existed instead. The Planck satellite, launched by the European Space Agency in 2009, mapped the temperature of this ancient radiation with extraordinary precision. The resulting images, you've probably seen them, often displayed in false color showing warmer and cooler regions, reveal structure. Not random noise, structure. Warmer patches correspond to regions that were slightly denser in the early universe. Cooler patches correspond to regions that were slightly less dense. The pattern isn't uniform, it has features, scales, harmonics, a specific signature that physicists can analyze, measure, decode. And what those measurements tell us is impossible. Those tiny variations didn't smooth out, they grew. How? Gravity, but not the way you might think. Not gravity as a stabilizing force, pulling things into equilibrium. Gravity as an amplifier, a positive feedback loop that takes small differences and makes them enormous. Here's how it works. Take a region that's slightly denser than average, 1 part in 100,000 denser, barely distinguishable from its surroundings. This region has slightly more mass than the space around it, which means it has slightly stronger gravity. That stronger gravity pulls on nearby matter, slowly at first, imperceptibly, but it pulls. Particles drift inward, gas flows toward the denser region, and as matter accumulates, as the region gains mass, its gravity strengthens. Stronger gravity pulls more matter. More matter creates stronger gravity. The cycle accelerates. Meanwhile, the surrounding regions, the ones losing matter, become less dense. Their gravity weakens. They pull less effectively on nearby matter, which means they lose even more material to neighboring denser regions. The dense get denser. The empty get emptier. This isn't a flaw in the system. It's how gravity fundamentally operates. Gravity doesn't smooth differences, it magnifies them. It takes variations and drives them toward extremes. And it works relentlessly, patiently, across billions of years. Think of it like this. Imagine a perfectly flat field after a light rain, with tiny, shallow puddles scattered across it. If you tilt the field even slightly, water flows from the high spots toward the low spots. The puddles grow deeper. The high spots dry out. The contrast increases. Now imagine the field itself reshaping based on where the water collects. Depressions forming where puddles gather, making those areas pull even more water. Hills rising where water has drained away, making those areas shed even more. That's gravity operating on cosmic scales. The universe was never stable. Those 1 part in 100,000 variations were never going to average out, never going to disappear. They were always going to grow, always going to separate the cosmos into regions of matter and regions of absence. The cosmic microwave background captures the moment just before this process began in earnest. The ripples, the seeds, the tiny imperfections that would become the cosmic web. But here's what makes this truly disturbing. Those variations weren't imposed from outside. They weren't added to the universe by some external force. They were inherent, built into the fabric of reality from the first moments of existence, arising from quantum fluctuations in the earliest fraction of a second after the Big Bang. Emptiness wasn't something that happened to the universe later. It was written into the initial conditions. The mathematics is brutal in its clarity. Physicists can take the pattern of temperature variations seen in the cosmic microwave background, those ripples measured by the Planck satellite, by WMAP before it, by COBE before that, and run them forward, in time using nothing but gravity and the known properties of matter and dark matter. No free parameters, no adjustments, just the laws of physics applied consistently across billions of years. What emerges from those simulations? The cosmic web, filaments, walls, voids, the exact large-scale structure we observe today. The galaxies in the simulations cluster along filaments in precisely the way real galaxies cluster. The voids in the simulations occupy the same fraction of volume as real voids. The pattern matches, not approximately, not in broad strokes, in detail. This means something profound. The emptiness we see today, the voids occupying 90% of the observable universe, the thin filaments where galaxies gather, the architecture of absence, all of it was determined 13.8 billion years ago by variations smaller than 1 part in 100,000. Inevitable. Inescapable. Uniformity was never an option. A smooth, evenly filled universe was never possible. The moment gravity began operating on those tiny density differences, the outcome was sealed. Matter would gather in some places, emptiness would expand in others, structure would form, and the contrast would deepen over time, driven by the same force, gravity, working without pause, without intention, without choice. You can see this in the numbers, in the measurements. The cosmic average density today is roughly 1 hydrogen atom per 10 cubic meters, but that average is meaningless. In galaxy clusters, the density can reach millions of atoms per cubic meter. In the deepest voids, the density drops to 1 atom per 1,000 cubic meters or less. The universe has sorted itself, segregated, pulled matter into concentrated nodes and left vast regions nearly empty. And this process began almost immediately, not billions of years after the Big Bang, not millions. Within the first 100 million years, a cosmic eye blink, the first density peaks were already collapsing, forming the precursors to galaxies. The first voids were already expanding, evacuating matter into the growing filaments. By the time the first stars ignited, roughly 200 million years after the Big Bang, the cosmic web already existed in crude form. Galaxies were already clustering. Voids were already dominant features. The universe never had a uniform phase. It went directly from nearly uniform to structured, from subtle variations to stark contrasts, from potential emptiness to actual emptiness. And every measurement confirms this. Every survey, every simulation, every detailed map of the cosmic microwave background. The architecture of absence isn't something that happened to the universe. It's how the universe had to unfold given the laws of physics and the initial conditions. So now we understand why matter never filled the universe. Because gravity doesn't fill. Gravity sorts. It takes small differences and drives them toward extremes. It gathers matter in some places and abandons it in others. It creates structure by creating absence. The 1 part in 100,000 variations in the cosmic microwave background guaranteed this outcome. The moment those fluctuations existed, the moment gravity began operating on them, the formation of voids became inevitable. But understanding why emptiness formed doesn't tell us how it continues, because voids aren't static. They're not frozen relics of the early universe, unchanging monuments to past processes. They're active, growing, expanding. Right now, as galaxies fall toward each other along filaments, the voids between them are growing larger. The contrast is sharpening. The universe is becoming more empty over time, not less. What drives this? What mechanism allows empty regions to expand while dense regions contract? The answer is gravity again, but gravity working in a way that seems impossible, a way that violates our everyday intuition about how attraction should operate, because somehow gravity doesn't just gather matter, gravity creates voids. Gravity creates emptiness. That sentence shouldn't make sense. Gravity is attraction, the fundamental force that pulls matter together, that holds planets in orbit, that binds galaxies. Gravity gathers, accumulates, concentrates. It's the force that builds structure, that assembles mass into stars and black holes and galaxy clusters. How can the same force that pulls matter together also evacuate space? It seems like a contradiction, like saying heat causes freezing or light creates darkness. Two opposite effects from a single cause. But it's not a contradiction. It's the most important mechanism in cosmic structure formation, the reason voids exist, the reason emptiness dominates the universe. And once you see how it works, you can't unsee it. Every image of the cosmic web, every galaxy survey, every simulation becomes a map of this process in action. Gravity doesn't just create voids despite gathering matter. It creates voids because it gathers matter. The two processes are inseparable. Return to the early universe for a moment. 380,000 years after the Big Bang, matter distributed almost uniformly across space, with those tiny 1 part in 100,000 density variations scattered throughout. We know what happened next. Gravity amplified those variations. Dense regions attracted more matter. The rich got richer. But here's what we didn't examine closely enough. Where did that matter come from? When a dense region pulls gas and dark matter toward itself, those particles have to travel from somewhere. They don't appear from nothing. They move. They flow. They migrate across vast distances from the surrounding space into the growing concentration. And when they leave something behind. Emptiness. Picture this. Imagine a city during a gold rush, when word spreads of a strike in the mountains. People don't teleport to the gold fields. They walk, they travel, they abandon their homes in the lowlands and move toward the promise of wealth in the high country. The mountains fill with prospectors. The valleys empty. The same population, different distribution. That's what gravity does to matter on cosmic scales. A region that starts slightly denser begins pulling matter from its surroundings. Gas flows inward. Dark matter streams toward the gravitational center. Over millions of years, over hundreds of millions of years, particles migrate from the less dense regions into the more dense ones. The migration creates two simultaneous effects. The dense region grows denser, obvious, expected, but the surrounding regions, the ones losing matter, become less dense, not gradually, progressively. The more matter they lose, the weaker their gravity becomes. The weaker their gravity, the less they can hold on to remaining matter. The less matter they have, the more easily neighboring dense regions strip it away. It's a feedback loop running in both directions. Dense regions grow denser, empty regions grow emptier. The universe sorts itself through selective migration, and what starts as a barely detectable variation becomes a chasm. The Botha's void, that enormous empty region stretching 330 million light-years, didn't form because matter was destroyed there. It formed because matter left, flowed outward toward the denser filaments surrounding it, migrated over hundreds of millions of years, responding to the gravitational pull of growing galaxy clusters. And here's the disturbing part. This process is still happening. You can measure it. Astronomers studying the motion of galaxies, using spectroscopy to measure their velocities, tracking their movement through space over decades, have detected systematic flows on enormous scales. Galaxies aren't moving randomly. They're moving coherently, streaming along filaments toward dense nodes, falling into galaxy clusters, following the gravitational landscape shaped by dark matter and ordinary matter combined. These flows have names. The Great Attractor, a gravitational anomaly in the direction of the constellations Hydra and Centaurus, pulling our local group and thousands of other galaxies toward it at hundreds of kilometers per second. The Shapley concentration beyond it, an even larger mass pulling the Great Attractor itself, fast enough to cross the United States coast to coast in under 10 seconds, fast enough to circle Earth in less than 2 minutes. And if that motion had started when humans first built cities in ancient Mesopotamia, it would have carried those galaxies roughly 94 trillion kilometers. That distance is so big, you could travel to our nearest star, Alpha Centauri, and still make it back home. Across cosmic distances, it's barely noticeable, a crawl, a drift, but it never stops. And every particle that falls toward a dense region is a particle that leaves somewhere else. Every galaxy streaming toward the Shapley concentration is a galaxy abandoning the space between structures. Every atom pulled into a filament is an atom evacuated from a void. The voids are expanding not because space itself is stretching, though that's also happening, but because matter is actively leaving them. Imagine standing in a vast stadium as the crowd evacuates after a game. You're not moving, you're standing still. But the density around you drops, decreases. The distance to the nearest person grows, not because anyone is pushing you away, but because everyone else is moving toward the exits. You become isolated through their departure. That's what's happening to matter in voids. The particles that remain, and some remain always, grow farther apart, not because they're moving away from each other, but because most of their neighbors have already left, pulled by gravity toward denser regions. But here's where it gets stranger. The voids themselves participate in this process. In the late 1990s, a team of astronomers led by Rien van de Veegaert at the University of Groningen began studying void expansion in detail using simulations and observational data. What they found violated intuition. Voids don't just sit passively as matter evacuates them, they grow, actively. Their boundaries expand outward over time, pushing into the surrounding filaments and walls like bubbles inflating in a foam. How? Through the absence of gravity. In regions where matter has mostly evacuated, where density has dropped to a few atoms per 1,000 cubic meters, gravity is weak, almost negligible. There's not enough mass to produce significant gravitational pull, which means there's nothing to resist cosmic expansion. The expansion of space, driven by the Big Bang, accelerated by dark energy, affects all regions. But in bound systems like galaxies, like galaxy clusters, gravity holds matter together tightly enough to counteract expansion. The Milky Way isn't expanding. The local group isn't expanding. The Virgo cluster isn't expanding. But voids have no such anchor. In voids, expansion operates unopposed. Space stretches. Distances grow. The sparse matter that remains spreads farther apart, not because it's moving through space, but because space itself is elongating between particles. And this creates an acceleration effect. The emptier a region becomes, the faster it expands. The faster it expands, the more difficult it becomes for matter from surrounding regions to fall back into it. The void's boundaries push outward, not because they're moving, but because the space inside is growing. Dense regions contract under gravity. Empty regions expand under cosmic expansion. The contrast sharpens. If you could watch a void evolve across billions of years, time-lapse the universe from the first galaxies until now, you'd see it breathing, swelling, growing like a cavity in foam, pushing against the filaments surrounding it, carving out larger and larger volumes of near emptiness while galaxies cluster more, tightly along its borders. Gravity creates the void by evacuating matter. Expansion makes the void permanent by preventing matter from returning. Two forces, two mechanisms, one outcome, emptiness as a structural feature of the cosmos. So gravity doesn't fill the universe, it empties it. By gathering matter in some places, it abandons matter in others. By creating dense nodes and filaments, it hollows out the space between them. Structure and emptiness arise together, two sides of the same process, inseparable. And the process accelerates. The denser a region becomes, the more powerfully it pulls matter from its surroundings. The emptier a region becomes, the faster it expands, and the harder it is for matter to return. Every million years that passes sharpens the contrast, makes the cosmic web more extreme, concentrates matter into thinner filaments, expands voids into larger volumes. What we see today is not the final state. It's a snapshot of an ongoing transformation. The universe is becoming more empty over time, not less. The architecture is growing more pronounced. But there's something else accelerating this process, something we haven't fully accounted for yet, because cosmic expansion isn't constant, it's not steady. Over the past several billion years, expansion has been accelerating, speeding up, driven by a force we barely understand, a force that makes up more than 2/3 of the universe's total energy density. We call it dark energy. And dark energy doesn't just expand space, It deepens isolation, widens the gaps between galaxies, pushes the voids farther apart, and makes the emptiness more permanent with every passing moment. The universe isn't just sorting itself through gravity, it's stretching itself apart through expansion, and the stretching is getting faster. There are distances in the universe that increase without anything moving. No galaxies traveling, no stars shifting position, no particles drifting through space. Just distance itself, growing, stretching, expanding like the gap between two marks on an inflating balloon. This is cosmic expansion, not a force pushing galaxies apart, but space itself elongating between them. And it's not a theory, it's a measurement, a phenomenon we can detect, quantify, track across billions of years. Edwin Hubble discovered it in 1929, analyzing the light from distant galaxies at Mount Wilson Observatory in California. He found that galaxies were receding from us, their light stretched toward redder wavelengths by their motion, and the farther away a galaxy was, the faster it appeared to be moving. Not because galaxies far away were somehow traveling faster through space, because space itself was expanding, carrying galaxies along with it like debris in a river's current. We've refined that measurement over the decades. The Hubble Space Telescope, the Planck satellite, surveys of distant supernovae. All of them confirm the same thing. The universe is expanding, has been expanding since the Big Bang, and shows no sign of stopping. But here's what most people don't grasp about expansion. It doesn't just move galaxies farther apart. It amplifies emptiness, makes voids larger, widens the gaps between structures. And it does this more effectively in empty regions than anywhere else. Expansion doesn't fill the universe, it evacuates it. Let's be precise about what expansion means. Space isn't a container. It's not a box holding galaxies, not a stage where cosmic events unfold. Space is a thing, a fabric, a field, something that can stretch and curve and distort. When we say space expands, we mean the metric of space itself changes. The distance between 2 points increases, even if those points aren't moving through space. Think of it this way. Take a rubber band and mark 2 dots on it with a pen. Now stretch the rubber band. The dots move farther apart, but they didn't travel across the surface of the rubber. The surface itself elongated beneath them. That's cosmic expansion, and it's happening everywhere, right now, between galaxies, between galaxy clusters, in the voids, even in this room, though the effect is so small, so completely overwhelmed by the electromagnetic forces holding atoms together, that you'll never measure it. The expansion rate, called the Hubble constant, tells us how fast this stretching occurs. Current measurements put it at roughly 70 kilometers per second per megaparsec. That's about 43 miles per second per megaparsec. What does that mean in human terms? Take 2 galaxies separated by 1 megaparsec, about 3.3 million light-years. Due to expansion alone, the distance between them increases by 70 kilometers every second, not because they're moving, but because space is growing. If those galaxies were separated by 10 megaparsecs, the distance would increase by 700 kilometers per second. 100 megaparsec separation? 7,000 kilometers per second. The effect scales with distance. Double the separation, double the expansion rate. Farther galaxies separate faster, not because they're accelerating through space, but because there's more expanding space between them. And here's the critical detail. Expansion affects empty regions differently than it affects dense ones. Picture 2 scenarios. First, a galaxy cluster. Thousands of galaxies bound together by gravity orbiting a common center of mass. The gravity in this system is strong, overwhelming. It holds galaxies in place despite cosmic expansion. The Virgo cluster, the Coma cluster, the Norma cluster, all of them remain gravitationally bound. Their internal distances aren't increasing. Expansion tries to pull them apart, but gravity resists. Expansion loses. Now, picture a void. The Booter's void, 330 million light-years across, containing perhaps 60 galaxies. The average density is roughly 1 hydrogen atom per 10 cubic meters, 1,000th of the cosmic average. Gravity in this region is weak, almost negligible. When expansion tries to stretch distances in the void, there's nothing to resist it. No gravitational anchor, no bound system fighting back. Space simply expands, unopposed, increasing the distance between the sparse galaxies, spreading the few remaining atoms farther apart. Expansion wins. This creates an invisible sorting mechanism operating across the cosmos. In dense regions, filaments, walls, galaxy clusters, gravity counteracts expansion. Matter stays bound. Distances remain relatively stable or even decrease as galaxies fall toward each other. The cosmic web contracts in these areas. In empty regions, voids, the spaces between filaments, expansion operates freely. Distances grow. Whatever, matter remains spreads thinner. The voids inflate like bubbles in rising dough. Over time, over billions of years, this differential effect amplifies the contrast. Dense regions resist expansion and grow denser through gravitational collapse. Empty regions surrender to expansion and grow emptier through stretching. The architecture sharpens. The universe doesn't just maintain its structure, it enhances it, and the data proves this is happening. Measurements of void growth from galaxy surveys, the Sloan Digital Sky Survey, the 2-degree field survey show that large voids are expanding measurably faster than the cosmic average. Some voids grow their radius by several percent per billion years, purely through expansion. Meanwhile, galaxy clusters show no such growth. They remain bound. The universe is sorting itself into extremes, islands of matter, oceans of nothing, and expansion is the force making it permanent. But expansion isn't uniform across cosmic history. For the first several billion years after the Big Bang, expansion was slowing, decelerating. The gravitational pull of all the matter and dark matter in the universe was acting as a brake, gradually reducing the expansion rate. Physicists expected this. It made sense. Gravity pulls inward. Expansion drives outward. Gravity should win eventually, or at least slow expansion to a crawl. Then, in 1998, 2 independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Riss, made a discovery that changed everything. They were measuring distant supernova, using them as standard candles to map cosmic expansion over time. Type 1. A supernovae explode with consistent brightness, which means astronomers can use them to calculate distance. By comparing distance to redshift, you can measure how expansion has changed over billions of years. The teams expected to find expansion slowing down. Instead, they found it speeding up, accelerating. Distant supernovae were farther away than they should be if expansion were constant or decelerating, which meant expansion must have accelerated in the time since that light left those galaxies. Something was pushing space to expand faster, overcoming gravity, driving galaxies apart with increasing velocity. They called it dark energy, not because they understood it, we still don't, but because it behaves like an energy field permeating space itself, creating a kind of repulsive pressure that counteracts gravity on the largest scales. And dark energy dominates. It makes up roughly 68% of the universe's total energy density. More than dark matter, more than ordinary matter, more than radiation, everything else combined. What does this mean for emptiness? It means voids don't just expand, they expand faster over time. Accelerating expansion amplifies the effect. The gaps between galaxies widen more quickly now than they did a billion years ago, more quickly than they will a billion years from now. You can see this in your mind if you shift perspective. Imagine watching the universe from outside time, seeing it evolve across billions of years in fast forward. In the early universe, galaxies are relatively close together, the cosmic web tightly packed. As time advances, the web stretches, filaments thin, voids inflate. Galaxies drift farther apart along the filaments, while the gaps between filaments grow enormous. Now accelerate that drift, make it speed up over time. That's accelerating expansion. That's dark energy. That's the universe we actually inhabit. And here's what that means in concrete terms. Galaxies that are currently within our observable universe, galaxies we can see whose light has reached us, will eventually cross a boundary beyond which their light can never reach us again. Not because they're moving faster than light through space, but because the expanding space between us grows, too quickly for light to traverse it. Regions of the universe are becoming unreachable, permanently. Isolation isn't just growing, it's becoming absolute. So expansion doesn't just preserve emptiness, it amplifies it. Every second, distances in voids increase by hundreds of kilometers. Every year, by billions of kilometers. Every million years, by trillions upon trillions. The effect is small on human scales, invisible across a single lifetime, but relentless across cosmic time. And it's accelerating. The universe today is more empty than it was a billion years ago. A billion years from now, it will be more empty still. Galaxies that currently share the same filament will drift too far apart to interact. Galaxy clusters that currently orbit each other will lose contact. The cosmic web will stretch until the filaments themselves dissolve into isolated islands. We're witnessing a transformation, not sudden, not violent, just inexorable. Matter clustered by gravity, emptiness expanded by the stretching of space itself. And now, accelerating expansion driven by dark energy, a force we barely understand, is making that emptiness not just permanent, but ever-growing. But dark energy isn't finished changing the universe, because if expansion continues accelerating, if dark energy remains constant or strengthens over time, the isolation we see today is only the beginning. The gaps between galaxies will widen beyond comprehension. Light from distant structures will redshift into invisibility. The observable universe will shrink, not because space itself is contracting, but because accelerating expansion will push more and more of the cosmos beyond our cosmic horizon. Future observers, billions of years from now, will look out and see less than we see today. Fewer galaxies, emptier skies, a universe that appears smaller, darker, more isolated with every passing eon. What does that isolation mean? What happens when galaxies drift so far apart that they can never, again, affect each other, never exchange light or matter or information? What happens when the universe becomes not just empty, but silent? The universe is tearing itself apart, not violently, not catastrophically, but inexorably. Galaxies are separating faster now than they were a billion years ago, faster than they will be a billion years from now. The expansion of space isn't slowing down as gravity tries to pull everything back together. It's speeding up. This shouldn't be possible. Every massive object in the universe, every star, every planet, every particle of gas, every atom of dark matter, exerts gravitational attraction on every other massive object. Gravity pulls inward, always. It should slow expansion, maybe even reverse it eventually, causing the universe to collapse back on itself in a big crunch. Instead, something is pushing space to expand faster. We call it dark energy, not because it's dark in the sense of blocking light, but because we don't know what it is. We can measure its effects, we can quantify its strength, we can detect its fingerprints in data from multiple independent sources. Distant supernovae, the cosmic microwave background, galaxy surveys spanning billions of light years, but we cannot explain it. We don't know what dark energy is made of, where it comes from, why it exists, or why its strength appears constant across cosmic time. We only know what it does. It drives galaxies apart. it deepens voids, it stretches the silence between structures, and it's winning. Let's start with what we actually know, not speculation, not theory, but measurement. In 1998, 2 teams of astronomers were studying Type 1a supernovae, stellar explosions that occur when white dwarf stars reach a critical mass and detonate. These supernovae are useful because they explode with remarkably consistent brightness. If you know how bright a supernova actually is, and you measure how bright it appears from Earth, you can calculate its distance with precision. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were using this technique to map cosmic expansion across billions of years. They observed supernovae in distant galaxies, comparing their distances to their redshifts. They expected distant supernovae to be slightly closer than predicted if expansion were constant. Because gravity should slow expansion over time, pulling galaxies back together, making the universe's expansion history different from a simple straight line. The data showed the opposite. Distant supernovae were farther away than expected, which meant the universe had expanded more than it should have if expansion were constant or decelerating. The only explanation, expansion was accelerating, had been accelerating for the past several billion years. Both teams published their results independently. Both reached the same conclusion. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics. But supernovae were just the beginning. The Planck satellite, launched by the European Space Agency in 2009, mapped the cosmic microwave background with extraordinary precision. The pattern of temperature fluctuations, those tiny variations from the early universe, contains information about the total energy content of the cosmos. The analysis revealed that ordinary matter makes up less than 5% of the universe's total energy density. Dark matter accounts for roughly 27%, and the remaining 68%, more than 2/3 of everything, is dark energy. Large-scale structure surveys confirm this. The distribution of galaxies across billions of light years, the way they cluster along filaments, the sizes and shapes of voids, all of it matches predictions made assuming dark energy exists with a measured strength. 3 independent lines of evidence: supernovae, the cosmic microwave background, galaxy surveys, all pointing to the same conclusion. Something is making the universe expand faster, and that something dominates the cosmos. But understanding that dark energy exists doesn't tell us what it means. Here's what it means. Imagine you're standing in a vast field with friends scattered around you. Some are close, a few meters away. Others are distant, hundreds of meters, kilometers. Now, imagine the ground itself begins stretching. Everyone moves away from everyone else, not because they're walking, but because the ground between them is expanding. At first, the stretching is slow. You can still see your distant friends. You could still walk to them if you tried, though it would take longer than before. But then the stretching accelerates. The ground expands faster. Your distant friends move away more quickly. Soon they're receding faster than you can walk, then faster than you can run, then faster than any speed you could possibly achieve. Eventually, you can't reach them anymore. Not because they're moving through space, but because space itself is expanding too quickly for you to traverse it. That's what accelerated expansion does to galaxies. Right now, galaxies beyond a certain distance, roughly 14.5 billion light-years from us, are receding faster than the speed of light. Not through space, but because the space between us expands at that rate. Light leaving those galaxies toward us is swimming upstream against expanding space, making progress but slowly, taking billions of years to traverse distances that grow as the light travels. But as expansion accelerates, something changes. Galaxies beyond a certain boundary, called the cosmic event horizon, are receding so quickly that light leaving them now will never reach us. Ever. Not in a trillion years. Not in a Google years. Never. The light will travel toward us, space will expand faster. The light will make progress but always lose ground. Like running on a treadmill that accelerates faster than you can run, you move forward, but the treadmill carries you backward faster and you never reach the edge. Those galaxies are gone, permanently unreachable, and the boundary is shrinking. Picture this. You're an observer in the far future, 1 trillion years from now, looking out at the night sky from a planet orbiting a star in the Milky Way. What would you see? Not the cosmic web, not the thousands of galaxies visible today through telescopes, not even the nearest galaxies like Andromeda or the Magellanic Clouds. You would see almost nothing. By then, accelerated expansion will have carried most galaxies beyond the cosmic event horizon. Their light, stretched by expansion, will have redshifted into invisibility. The photons will still exist, still travel through space, but they'll be stretched to wavelengths so long, radio waves, then longer, then undetectable, that no telescope could capture them. The observable universe will have shrunk, not because space contracted, but because accelerating expansion pushed everything beyond reach. You'd see a few nearby galaxies, the ones gravitationally bound to the Milky Way, merged into a single enormous elliptical galaxy through billions of years of collisions. Everything else would be darkness, silence, emptiness so complete it would seem the universe contained only your galaxy and nothing else. And here's what makes this truly disturbing. Those future observers wouldn't know they were missing anything. They'd have no way to detect the billions of galaxies that exist beyond their horizon. No evidence of the cosmic web. No trace of the Big Bang's expansion, since their entire observable universe would be a single bound system. They'd look out and see permanent, eternal, absolute emptiness, and they'd think that's all there ever was. But we can see more. We exist in a narrow window of cosmic history when the universe is old enough to have formed complex structures, but young enough that most of those structures remain visible. We can see the cosmic web before it dissolves. We can measure expansion before it carries everything away. We can study the universe before silence becomes absolute. How long do we have? The math is brutal. Within 100 billion years, longer than the current age of the universe, but a blink in cosmic terms, most galaxies beyond our local group will cross the event horizon. Within 1 trillion years, they'll all be gone from view. The universe is becoming a collection of isolated islands, galaxy clusters separated by voids so vast, expanding so rapidly that light can never cross them. Each island alone in darkness, unable to interact, unable to exchange information, unable to even know the others exist. Emptiness won't just dominate the universe, it will become total. So dark energy doesn't just expand space, it severs connections. It takes a universe that was already mostly empty and makes it more so. It takes voids that were already enormous and inflates them beyond comprehension. It takes galaxies that were already isolated and pushes them beyond all possibility of contact. And it never stops. Every second, the cosmic event horizon shrinks slightly. Galaxies that were observable yesterday cross the boundary today. Light that was making progress toward us loses ground. The universe we can see contracts even as the universe itself expands. This is what dark energy means. Not just expansion. Permanent, accelerating, irreversible isolation. But there's something else happening simultaneously. Something we haven't fully addressed yet. Because while dark energy pushes galaxies apart, while expansion empties the voids, while the cosmic web stretches toward dissolution, the galaxies themselves are changing, stars are aging, fuel is being consumed. The rate of star formation, the birth of new stars from gas and dust, has been declining for billions of years. The universe isn't just becoming emptier through expansion, it's becoming darker through stellar exhaustion. And that darkness has its own timeline, its own inexorable progression. A timeline that ends not with explosion, but with silence. There's a graph that astronomers don't often show the public, not because it's controversial, not because the data is uncertain, but because it tells a story most people don't want to hear. A story about endings, about decline, about the universe growing darker without violence, without explosion, without any catastrophic event to mark the transition. The graph shows star formation rate across cosmic history. The vertical axis measures how many solar masses of new stars are born per year in an average galaxy. The horizontal axis spans time from the Big Bang to today, roughly 13.8 billion years, and the line slopes downward, steeply at first, peaking around 10 to 11 billion years ago, when the universe was young and gas-rich and galaxies blazed with stellar nurseries, then gradually declining, falling, dropping to a fraction of its peak value. Today's star formation rate is roughly 3% of what it was at the universe's brightest moment. 3%. The universe is still making stars. The Orion Nebula glows with newborn suns. The Tarantula Nebula in the Large Magellanic Cloud hosts thousands of young massive stars. But these are exceptions, rare pockets of activity in a cosmos that is, on average, growing quieter. And the decline continues, not suddenly, not catastrophically, just inexorably year after year, millennium after millennium, the rate drops. Stars still form, but fewer of them. Galaxies still shine, but more dimly. The universe is fading, not all at once, not through any dramatic event, through something far more unsettling, simple, patient, unstoppable exhaustion. To understand why the universe is dimming, you need to understand what stars actually are. Not eternal lights, not permanent fixtures in the sky. Stars are machines that convert matter into energy through nuclear fusion. They consume fuel, primarily hydrogen, and produce light, heat, heavier elements. They burn, and like anything that burns, they require continuous supply. The fuel comes from gas, vast clouds of hydrogen and helium scattered through galaxies, remnants from the Big Bang, enriched over time with heavier elements forged in previous generations of stars. These clouds collapse under their own gravity, fragmenting into smaller clumps, heating up as they compress until the core reaches 10 million degrees Kelvin and fusion ignites. A star is born, but the process requires specific conditions. The gas must be dense enough to collapse, cold enough to resist pressure, massive enough to reach fusion temperature, and it must exist in regions where it can actually gather, in galaxy disks, in spiral arms, in places where density waves compress the medium and trigger formation. For most of cosmic history, these conditions were common. The early universe was filled with gas. Galaxies formed from enormous reservoirs of hydrogen, far larger than the galaxies themselves. The Milky Way, for instance, formed from a cloud containing perhaps 10 times more mass than the galaxy holds today. Most of that mass became stars. Some was expelled. Some fell into the central black hole. But there was abundance. Abundance allowed extravagance. During the peak epoch of star formation, 10 to 11 billion years ago, when Earth had not yet formed and the Sun did not exist, galaxies were producing stars at prodigious rates, hundreds of solar masses per year in large galaxies, thousands in the most extreme cases. The universe blazed, but abundance is finite. Here's what astronomers discovered when they surveyed galaxies across different cosmic epochs, comparing nearby galaxies to distant ones, measuring their star formation rates and gas content. The gas is disappearing. Not destroyed. Matter cannot be destroyed, only transformed. But gas that could become stars is being converted into forms that cannot. Stars themselves lock away hydrogen in their cores. Massive stars explode as supernovae, ejecting gas into intergalactic space where it becomes too hot, too diffuse to collapse again. Black holes accrete gas and convert some of it into radiation that heats surrounding clouds, preventing further star formation, and some gas simply leaves. Galactic winds, driven by supernova, by stellar radiation, by jets from supermassive black holes, push gas out of galaxies entirely. The Hubble Space Telescope has captured images of these outflows, vast streams of material escaping into intergalactic space at thousands of kilometers per second. Once expelled, that gas rarely returns. The supply dwindles. Measurements from radio telescopes mapping neutral hydrogen, from infrared observatories detecting molecular clouds, from surveys of nearby galaxies all point to the same conclusion. Galaxies today contain far less star-forming gas than galaxies in the past. The Milky Way has enough gas to sustain current star formation rates for perhaps another few billion years, maybe 10 billion at the outside. After that, the reservoir will be essentially depleted. And we're not unique. Across the observable universe, in galaxy after galaxy, surveyed by instruments like the Atacama Large Millimeter Array, the Herschel Space Observatory, the Very Large Telescope, the pattern repeats. Gas content declining, star formation dropping, the fuel running out. But here's what makes this different from everything we've discussed so far. This isn't about expansion. It isn't about voids growing or galaxies separating. This is internal. This is galaxies themselves changing, using up their resources, aging. The universe isn't just becoming emptier through space stretching, it's becoming darker through time passing. In 2014, an international team of astronomers published results from a multi-year survey studying star formation across cosmic time. They combined data from multiple telescopes, ground-based observatories, the Hubble Space Telescope, infrared satellites. They measured star formation rates in hundreds of thousands of galaxies, spanning 11 billion years of cosmic history, from the peak epoch to the present day. The lead researcher was David Sobral from Leiden University in the Netherlands. When he compiled the final graph, when he saw the complete picture of star formation decline laid out across billions of years, he later described it as looking at the universe's biography, watching it age in real time. The peak was clear, unmistakable, roughly 11 billion years ago. Since then, steady decline. What this means in human terms is startling. If you could watch the universe in time-lapse, speeding through billions of years in minutes, you'd see galaxies brighten during the early epochs, blazing with blue-white light from massive young stars. Spiral arms would glow intensely. Star clusters would pepper galaxy disks like scattered jewels. Then gradually, the light would dim. Not uniformly. Some galaxies would still birth stars, but fewer. The blue-white glow would fade to yellow as massive stars died and weren't replaced, then to red as even smaller stars aged. Eventually, not for trillions of years, but eventually, new stars would stop forming entirely. Galaxies would contain only the stars that already exist, aging, cooling, burning through their remaining fuel. And here's the crucial detail that separates this from cosmic expansion. This process is irreversible. When a void expands, it's possible in principle for matter to flow back in if conditions changed. When galaxies separate, they could in principle approach again if expansion reversed. But gas converted into stars cannot become gas again. Hydrogen fused into helium, into carbon, into iron, cannot unfuse. The nuclear reactions run one direction. The fuel, once burned, is gone. The universe's brightening was temporary, a phase, a window when conditions allowed abundant star formation. That window is closing, so the universe grows darker, not through catastrophe, but through depletion. No explosion marks the transition. No dramatic event signals the change. Just galaxies slowly, quietly running out of the raw material needed to make new stars. The Milky Way will continue forming stars for billions of years yet, but each generation will be smaller than the last. Fewer massive stars, fewer stellar nurseries, more darkness between the points of light, and eventually the last star will form. Somewhere, in some galaxy, a final collapse of a final gas cloud massive enough to ignite fusion. It will shine for millions or billions of years depending on its mass, completely unaware that it represents an ending. Then no more. After that, the universe will contain only the stars that already exist, aging, dimming, burning through their remaining fuel until even they fade. But that's not the end of the story, because stars dying is only half the equation. The other half is what happens to the energy they release, the heat they produce, the light they emit. Where does it go? The answer involves a principle more fundamental than gravity, more universal than expansion, more inevitable than anything we've discussed so far. A principle that governs not just stars, not just galaxies, but every process in the universe, every motion, every reaction, every transformation of energy from one form to another. A principle that mathematicians and physicists call entropy. And entropy has its own timeline, its own inexorable progression, one that leads not to darkness alone, but to stillness. In 1850, a German physicist named Rudolf Clausius was studying heat engines, machines that convert thermal energy into mechanical work, when he discovered something that troubled him deeply. He noticed that every process he examined, every transformation of energy from one form to another produced waste, not because the machines were poorly designed, but because something fundamental in nature demanded it. Heat always flowed from hot objects to cold ones, never the reverse. Energy always dispersed. Concentrated forms became diffuse, and the transformation was irreversible. You cannot unscramble an egg. You cannot gather smoke back into wood. You cannot spontaneously collect scattered heat and concentrate it into a single point. The universe permits these processes to run in only one direction. Clausius called this principle entropy, and he realized with a kind of clarity that changes everything, that entropy always increases. In any closed system, over time, disorder grows, organization decays, concentrated energy spreads out until it becomes so diffuse, so evenly distributed that it can no longer do work. The second law of thermodynamics. Not a theory, not a hypothesis, a law, one of the most tested, most fundamental principles in all of physics. Every experiment ever conducted confirms it. Every observation supports it. It governs chemical reactions, stellar evolution, the expansion of gas, the flow of heat, the operation of every machine ever built, and it governs the fate of the universe. Because if entropy always increases, if energy always disperses, if structure always decays, then the universe has a direction, a trajectory, an end point. Let's be precise about what we're describing. Entropy is not chaos, it's not randomness. It's a measure of how energy is distributed within a system. Low entropy means concentrated, energy gathered in specific places, organized, capable of doing work. High entropy means dispersed, energy, spread evenly, disorganized, useless for driving processes. Think of it this way. Imagine a room with a single candle burning in the center. The candle represents concentrated energy, chemical bonds in wax releasing heat through combustion. The flame is hot, the surrounding air is cool, there's a temperature difference, an energy gradient. That gradient could, in principle, drive a tiny heat engine, turn a wheel, do work. Now, let the candle burn. Over hours, the flame consumes the wax. Heat radiates into the room. The air warms slightly, uniformly. Eventually, the candle burns out. The energy released hasn't disappeared. It's still in the room, heating the air molecules. But it's spread out, diffuse. The room's temperature is now uniform. No gradients exist. The energy is there, but it can no longer do anything. Entropy has increased. The universe operates the same way. Stars are candles. Concentrated energy sources burning fuel, maintaining temperature differences, driving processes. But stars burn out. Their energy disperses into space as radiation, heating the cosmic microwave background by infinitesimal amounts, spreading across vast distances until it becomes indistinguishable from the background itself. And unlike the processes we see every day, water freezing, plants growing, galaxies forming, which appear to create order from disorder, these are local decreases in entropy paid for by larger increases elsewhere. A plant growing decreases local entropy by organizing molecules into complex structures, but the sun powering that growth releases vastly more entropy through fusion, dispersing energy across the solar system. The net change is positive, always positive. On cosmic scales averaged over time, entropy wins, every time. Here's what makes this principle disturbing when you apply it to the universe. Every organized structure you see, galaxies, stars, planets, the cosmic web itself, represents a low entropy state. Matter concentrated in specific locations rather than spread uniformly. Energy gathered in massive objects rather than dispersed. Temperature differences between hot stellar cores and cold interstellar space. All of it temporary, not because these structures are fragile or unstable in the conventional sense. The sun will burn for another 5 billion years. The Milky Way will persist for trillions. But persist is not the same as permanent. Every star that burns converts low-entropy fuel into high-entropy radiation. Every supernova disperses concentrated matter across space. Every black hole that evaporates, and they all eventually evaporate through Hawking radiation, releases its organized mass energy as thermal radiation. The universe is spending its reserves. Physicists measuring entropy in various cosmic systems have found the same pattern everywhere. Star-forming regions have lower entropy than the diffuse interstellar medium. Young galaxies have lower entropy than old ones. The early universe had far lower entropy than the universe today. Entropy is increasing, globally, irreversibly, and there's no mechanism to reverse it. Gravity creates local order by pulling matter together, forming stars and galaxies. But this process increases entropy elsewhere, through the heat generated by compression, the radiation released by accretion, the energy dispersed during star formation. The second law remains unviolated. Expansion might seem to decrease entropy by creating more volume for energy to occupy, but it actually increases it, spreading matter and radiation across larger distances, reducing densities, eliminating gradients. Dark energy accelerates this dispersal, driving regions apart faster, ensuring they can never reconcentrate. Every force we've examined, every mechanism that shapes the cosmos, serves entropy in the end. Some create temporary local order, but the total always increases, which raises an uncomfortable question. If entropy always increases, if energy always disperses, if structure always decays, what does the universe look like when entropy reaches its maximum? When no more energy gradients exist, when every possible process has run to completion. The mathematics is unambiguous. A system in maximum entropy, what physicists call thermodynamic equilibrium, is a system where nothing changes, not because time has stopped, but because no energy gradients remain to drive change. Temperature is uniform everywhere. Particle velocities follow the same distribution. No hotspots exist to radiate, no cold sinks exist to absorb. Energy is evenly distributed across all available states. Motion continues, particles still move, photons still travel. But the motion accomplishes nothing. There's no net flow, no transformation, no work being done. A kind of stillness that isn't absence of movement, but absence of consequence. For the universe, this state has a shape. No stars forming because no density gradients exist to trigger. Collapse. No stars burning because all fuel has been consumed or dispersed. No black holes accreting because no matter streams toward them. Just radiation, Photons stretch to infinite wavelengths by eternal expansion, carrying negligible energy, contributing nothing to any process, and vast distances, incomprehensible distances, because accelerating expansion continues regardless of entropy. Even after the last star dies, even after the last black hole evaporates, space keeps stretching. The already enormous voids we see today become immeasurably larger. The already isolated galaxy clusters drift beyond all possible contact. In a maximum entropy universe, you could travel for billions of years at the speed of light and encounter nothing. No stars, no planets, no radiation energetic enough to detect. Just the cosmic microwave background, cooled to a fraction of a degree above absolute zero, stretched by expansion into wavelengths measured in light years. Darkness so complete it makes current voids seem crowded by comparison. Silence so absolute that the word silence fails to capture it. A darkness so complete it has weight. This isn't speculation. It's not one possible future among many. Given the second law of thermodynamics, given the measured expansion rate, given the observed properties of dark energy, this is the only possible future. Not in millions of years, not in billions. The timescale is staggering, 10 to the power of 100 years or longer before the last black holes evaporate. Time spans that make the current age of the universe seem like a heartbeat. But the direction is certain, the destination is known. The universe is moving toward maximum entropy, toward uniformity, toward a state where the tiny 1 part in 100,000 variations that seeded galaxies are erased, where the structure that took billions of years to form dissolves back into featureless uniformity. Emptiness, not just as a feature of the universe, but as its final condition, so time favors nothingness, not through violence, not through catastrophe, through the patient, inexorable operation of the second law. Energy disperses, structure decays, gradients flatten, and there's no force in nature that can prevent it, no mechanism that can reverse it, no process that can restore what entropy takes. Gravity gathered matter into galaxies for a while, but gravity cannot fight entropy forever. Dark energy drives expansion, accelerating dispersal. Stars burn, converting low-entropy fuel into high-entropy radiation. Black holes evaporate, releasing their mass as heat. Every process we've examined contributes to the same outcome. The universe began in a low-entropy state, matter and energy compressed, concentrated, organized. The Big Bang didn't create entropy. It created the conditions for entropy to increase, and it's been increasing ever since. 13.8 billion years of increasing entropy, 13.8 billion years of structure forming and dispersing, of energy concentrating briefly before spreading out again. But here's what we haven't addressed. We know the universe is expanding. We know entropy is increasing. We know dark energy is driving galaxies apart faster over time. But what does that combination actually mean for observation? For what future beings could see if they existed in that far future? Because isolation isn't just physical separation, it's informational. It's the loss of the ability to see, to measure, to know that anything else exists. And that loss is already happening. Right now, as we observe the universe, regions are crossing a boundary beyond which they become forever unreachable. Not just distant, unreachable. Their light will never arrive. Their existence will become unverifiable. The observable universe is shrinking, and what that means for the cosmic story, for the ability of any future observer to understand where they came from or what else exists, is more profound than anything we've discussed so far. Right now, at this moment, there are galaxies crossing a line they will never cross back. Not a physical line, not a barrier you could touch or see, a boundary in space-time itself, a threshold beyond which light emitted toward us will never arrive, no matter how long we wait. Not in 1,000,000 years, not in a trillion, never. These galaxies aren't being destroyed, they're not disappearing, they're simply moving beyond reach, carried by the expansion of space faster than light can swim upstream against that expansion, and once they cross that boundary, they're gone, permanently, irrevocably. This boundary has a name, the cosmic event horizon, and it's not theoretical, it's measurable. Physicists can calculate exactly where it lies, exactly which galaxies have already crossed it, exactly how many will cross it tomorrow, next year, next millennium. Lawrence Krauss and Robert Scherer, astrophysicists studying cosmic horizons, published calculations in 2007 showing that roughly 97% of the galaxies currently observable will eventually cross this boundary. Most within 100 billion years, some within a trillion, 97%. Almost everything we can see today will become unseeable, not darker, not fainter, absolutely invisible, beyond all possibility of detection. And this creates a consequence that goes far deeper than simple distance. Because when those galaxies cross the horizon, they don't just become unreachable, they take their information with them, their light, their history, their evidence that they ever existed at all. The universe isn't just becoming emptier through expansion, it's becoming unknowable. The term event horizon is familiar from black holes, the boundary beyond which nothing, not even light, can escape. Cross it and you're gone, severed from the rest of the universe by the warping of space-time itself. Cosmic event horizons work differently but produce the same result. They're created not by gravity warping space, but by expansion stretching it. And they exist because expansion is accelerating. The space between distant objects grows faster over time, driven by dark energy. Here's how it works. Take a photon of light, leaving a distant galaxy toward us. That photon travels at the speed of light through space, roughly 300,000 kilometers per second, fast enough to circle Earth 7.5 times in 1 second, fast enough to cross the solar system in hours. But the space between that galaxy and us is expanding, growing, stretching as the photon travels. If expansion were constant, the photon would eventually reach us. It would take billions of years, but it would arrive. The expanding space would slow its progress, but not stop it. But expansion isn't constant, it's accelerating, which means the space between us and that distant galaxy grows faster over time. The photon makes progress toward us. It moves through space normally, but the space ahead of it expands faster than the photon can traverse it. Imagine running on a treadmill that accelerates. At first, you make progress toward the front, but if the treadmill speeds up faster than you can run, you start losing ground. You're still running forward, still moving, but the belt carries you backward faster. You never reach the edge. That photon never reaches us. And here's what makes this permanent. The galaxy that emitted the photon continues receding. The space between us continues expanding, accelerating. Every second increases the gap. Every year makes it larger. Eventually, the galaxy crosses a distance, roughly 16 billion light-years in our current epoch, beyond which photons leaving it now will never reach us. That distance is the cosmic event horizon. Galaxies beyond it are lost, not destroyed, not annihilated, simply separated by so much expanding space that no signal they emit can ever cross the gap. Picture yourself as an observer in the far future, 100 billion years from now, 1 trillion years, standing on a planet orbiting a star, one of the last stars still burning, looking out at the night sky. What would you see? Almost nothing. By then, most galaxies visible today will have crossed the event horizon. Their light, stretched by expansion, will have redshifted into invisibility. The photons they emitted will have been stretched to wavelengths so long, radio waves, then longer, then undetectable, that no telescope could capture them. You'd see perhaps a few dozen galaxies, maybe 100, the ones gravitationally bound to your local group, merge through billions of years of interactions into a single enormous elliptical galaxy. Everything else, the thousands of galaxies visible through current telescopes, the billions mapped by surveys, the cosmic web spanning the observable universe, would be gone from view. But here's what makes this truly disturbing. You wouldn't know they were missing, because all evidence of their existence would have vanished with them. The light they emitted, the gravitational influence they exerted, the patterns in the cosmic microwave background that revealed them, all of it redshifted beyond detection, carried away by expansion, lost. If you were a cosmologist in that far future, studying the universe with the best instruments available, you would conclude that the universe contained only your galaxy. You'd measure the expansion of space and find it nearly undetectable. All the distant objects that reveal expansion through their recession would be gone. You'd look for evidence of the Big Bang and find none. The cosmic microwave background would be cooled and stretched into invisibility. You would think the universe was static, eternal, and essentially empty. A single island of stars surrounded by infinite void. And you'd be wrong, but you'd have no way to know you were wrong. The information that could prove otherwise would exist, technically. The galaxies would still be there, the light would still be traveling, but separated by so much expanding space that no observation could bridge the gap. This isn't hypothetical. Abraham Loeb at Harvard and Krauss at Arizona State University have published detailed studies of this scenario. They call it the end of cosmology, the point at which future observers lose the ability to reconstruct cosmic history because the evidence has literally moved beyond their horizon, and it's already begun. Let's put you there, not as an abstract observer, but as a physical being. You're standing on a world orbiting a dim red dwarf star, one of the last stars still burning in a universe 100 trillion years old. Your body, if you still had one, if anything biological could persist that long, would exist in near total darkness. The sky above you would be black, absolutely black. Not the black of a moonless night on Earth where stars still shine, the kind of black that has depth, weight. The absence of light so complete that your eyes, evolved to detect photons, would find nothing to register. You'd see your own galaxy, massive, aged, filled with red dwarf stars and white dwarf remnants. But beyond that, for billions of light years in every direction, nothing. No spiral galaxies, no star clusters, no nebulae glowing with new star formation, just void. And if you had instruments, if you could measure the expansion of space, you'd find it continuing, accelerating, the horizon shrinking closer over time, more space crossing the boundary every year, every decade, every eon. You would be witnessing isolation becoming absolute. So isolation doesn't mean destruction. The galaxies beyond the horizon still exist, still contain stars, planets, whatever structures they've evolved into over trillions of years. They haven't been erased. They haven't ceased to be. They've simply been separated by so much space that no interaction is possible, no light exchanged, no gravity felt, no information transmitted. And separation, on cosmic scales, is functionally identical to non-existence. If a galaxy exists but cannot be detected, cannot be measured, cannot affect anything in your observable universe, does it still exist in any meaningful sense? Not philosophically, practically, for the purposes of physics, of measurement, of knowledge. The answer is no. This is what accelerated expansion creates. Not a universe that ends, but a universe that fractures, that splinters into isolated islands, each containing its own galaxies, its own observers if any remain, each completely cut off from all the others, each island alone in its own darkness, unaware that other islands exist, unable to verify that anything exists beyond its shrinking horizon, emptiness as separation, as isolation, as the permanent, irreversible loss of contact. But there's something even more unsettling than isolation, Because isolation at least implies that things continue, that the islands remain, that stars still burn in them, that processes still unfold even if no one can observe them. What happens when those processes stop? When the last star burns out? When entropy completes its work and no energy gradients remain to drive change? What does a universe look like when nothing happens anymore? There will come a moment, impossibly far in the future beyond all human intuition about time, when the universe experiences its last event. Not an explosion, not a collapse, not anything dramatic or violent or worthy of the word event at all. Just a particle, a photon perhaps, or an electron, drifting through an expanse of space so vast, so cold, so empty, that the distance to the nearest other particle is measured not in light years, but in numbers that break the capacity of language to express. That particle will move, it will travel, and then eventually it will settle into a state from which nothing further can emerge. Not because it stops moving, particles never truly stop at the quantum level, but because its motion becomes meaningless, indistinguishable from every other particle's motion, statistically identical to stillness, and after that moment, nothing new will happen in the universe. Ever. Not for 1 trillion years. Not for a Google years. Not for any duration we have words to describe. The universe will continue existing. Time will pass, space will persist, but nothing will change. No transformations, no processes, no events. Physicists call this heat death, thermodynamic equilibrium, maximum entropy. The state where all possible processes have run to completion, all energy gradients have been eliminated, all differences have been erased, a universe that exists but does nothing. And what makes this particularly unsettling is that there's no threshold to cross, no boundary to mark the transition. The universe doesn't die suddenly. It fades, gradually, asymptotically approaching a state of complete stillness across timescales that dwarf the current age of the cosmos by factors that make infinity seem comprehensible by comparison. Let's be precise about what physicists mean when they describe the universe's thermodynamic end state. Not a state of zero energy. Energy cannot be destroyed. It can only change forms, disperse, become less concentrated. The total energy content of the universe in this final state would be the same as it is today, the same as it was at the Big Bang, but it would be distributed completely uniformly. Imagine that room from earlier chapters, the one with the candle burning. We described how the candle's concentrated chemical energy dispersed into heat, warming the air until the temperature became uniform. No gradients, no differences. Energy present, but useless for doing work. Now, expand that room to cosmic scales. Every cubic meter of space containing the same infinitesimal amount of energy. Every particle moving with velocities drawn from the same statistical distribution. Every photon stretched by expansion to wavelengths approaching infinity. Temperature everywhere hovering at a fraction of a degree above absolute zero. The second law of thermodynamics guarantees this outcome. Entropy increases, energy disperses, and given infinite time, or near infinite time, the distinction becomes irrelevant. Every system approaches maximum entropy. For stars, this means complete fuel exhaustion. The last stars will burn out roughly 10 trillion years from now, a time span during which Earth had not yet formed, life had not yet emerged, would be repeated 10,000 times over. Red dwarfs, the smallest, longest-lived stars, consuming their hydrogen so slowly that they'll outlast every other stellar type. But even they will die, their cores will cool, their light will fade, and eventually the last photon will leave the last star, travelling outward into darkness that will never again be interrupted. For black holes, it means complete evaporation through Hawking radiation. This process is slow almost beyond conception, A solar mass black hole would take 10 to the power of 67 years to evaporate completely. A supermassive black hole like Sagittarius A star at the center of the Milky Way would take 10 to the power of 100 years. But they will evaporate. They must. Hawking radiation is not theoretical speculation, but a firm prediction of combining quantum mechanics with general relativity. Every black hole emits thermal radiation, loses mass, shrinks. Given enough time, they all disappear. And when they do, they release their mass energy as random thermal radiation indistinguishable from the background. But here's what makes the final state truly strange. It's not absence of motion, it's absence of consequence. Particles still move in a maximum entropy universe. Photons still travel. Quantum fields still fluctuate. The laws of physics don't change. Time doesn't stop. Space doesn't freeze. But nothing happens. Because happening requires more than motion. It requires transformation, change of state, the conversion of one form of energy into another. And all of that requires energy gradients, hot regions and cold regions, dense areas and sparse areas, differences that can drive processes. In thermodynamic equilibrium, no such differences exist. Think of it this way. Picture a vast ocean on a perfectly calm day. No wind, no currents, no temperature differences between surface and depths. The water molecules are still moving. They vibrate. They shift position at the molecular level. But the ocean as a whole appears completely still. Nothing happens at the macroscopic scale because the molecular motions average out to zero net change. Now imagine that ocean is the universe, and instead of water molecules, it's every particle that exists, and instead of a calm day, it's eternity. That's thermodynamic equilibrium. Freeman Dyson, the physicist who spent decades studying the far future of the universe, described it in a 1979 paper as a universe in which nothing is left but gravity and incoherent radiation. He calculated that intelligent life could not persist in such conditions, not because the physical laws forbid it, but because intelligence requires energy flow to maintain structure, to process information, to think. And there's no energy flow in equilibrium. Brian Greene, describing this state in his work on cosmology, used the phrase, a frozen accident. The universe locked into a configuration from which no further evolution is possible. All processes complete, all reactions finished, all transformations exhausted. How long does it take to reach this state? The numbers become almost meaningless. The last stars burn out in 10 trillion years. The last black holes evaporate in 10 to the power of 100 years. After that, the universe enters what physicists call the dark era, a phase lasting perhaps 10 to the power of 100 to 10 to the power of 150 years, during which even the last remnants of structure dissolve. By the time Earth formed, dinosaurs had not yet appeared. That took another 4 billion years. The span from dinosaurs to today is another 65 million years. Stack timescales like this. Billions of years, then billions of those periods. And you don't even begin to approach the duration of the Dark Era. And even the Dark Era is not the final state. It's just the approach. Asymptotic. Forever getting closer but never quite arriving, because arriving would require a discrete transition, and thermodynamics operates on continuous gradients. But practically, functionally, for all purposes that matter, the universe reaches effective thermodynamic equilibrium, and then simply exists in that state, forever. We've travelled a long way together through this story. We began with the observation that most of the universe is empty. Not poetically empty, but measurably, quantifiably empty. 1 hydrogen atom per cubic meter. Voids occupying 90% of observable space. We discovered that this emptiness has structure, architecture, the cosmic web of filaments and walls surrounding enormous voids, shaped by gravity and dark matter. We learned that this structure emerged from tiny variations in the early universe. one part in 100,000 differences in density that gravity amplified into galaxies and voids. We saw how gravity creates emptiness by gathering matter in some places and abandoning it in others. How expansion makes that emptiness permanent by stretching space faster than matter can cross it. We confronted dark energy driving accelerated expansion, pushing galaxies beyond cosmic event horizons, creating isolation that becomes absolute as regions of space become permanently unreachable. We watch stars form and then fade, their birth rate declining across cosmic history as galaxies exhaust their gas supplies. We understood entropy increasing, energy dispersing, structure decaying through the patient operation of the second law of thermodynamics. We witnessed isolation becoming complete as the observable universe shrinks, as light from distant galaxies redshifts into invisibility, as future observers lose the ability to see evidence of cosmic history. And now we arrive at the final state, the endpoint all these processes have been driving toward since the beginning: stillness. Not the stillness of death. Death implies something that was once alive. Not the stillness of ending. Endings imply events, transitions, moments that can be marked. Just stillness as a physical condition, a state the universe approaches and maintains for all remaining time. Particles moving but accomplishing nothing. Photons traveling but carrying negligible energy. Quantum fluctuations occurring but averaged into uniformity. A universe that exists in a condition from which nothing further can emerge. The kind of silence that does not echo. So this is where physics leads us. Not to catastrophe, not to explosion or collapse, not to anything violent or dramatic, just to gradual, inexorable, patient decay into uniformity. Every force we've examined contributes to this outcome. Gravity gathers matter but increases entropy. Expansion spreads matter and eliminates gradients. Dark energy accelerates separation. The second law ensures dispersal. Stars exhaust their fuel, black holes evaporate, structures dissolve, all of it lawful, predictable, following rules we can write down, verify through experiment, trace forward through calculation, the universe trending toward simplicity, toward uniformity, toward a state where the tiny variations that seeded galaxies are completely erased, where the momentary complexity that gave rise to stars, planets, and life is smoothed back into featureless equilibrium, emptiness not just as a feature but as the final, permanent, unchanging condition. And this is where the terror actually lives, not in the mechanics, not in the physics, not in the laws themselves. They're neutral, indifferent, operating without intention or malice. The terror lives in meaning, in what this outcome implies about existence, about complexity, about the rare exceptions we call structure and life and thought. Because if the universe's natural state is equilibrium, if complexity and structure are just temporary disturbances, brief fluctuations before the inevitable return to uniformity, what does that make us? What does it mean that consciousness emerged, that thought exists, that questions can be asked in a universe destined for absolute stillness? The physics gives us the timeline, the mechanisms, the certainty that stillness comes, but it doesn't tell us whether that's catastrophic, whether it matters, whether the knowledge should fill us with dread or acceptance or something else entirely. That question doesn't have a physical answer. When most people hear about the heat death of the universe, they imagine an ending, a final moment, a cosmic tragedy, the last star flickering out in darkness while some hypothetical observer watches the universe die. They imagine loss, destruction, the terrible weight of finality pressing down on everything that exists. But that's not what heat death is. There is no moment when the universe ends, no transition you could witness, no event you could mark on a timeline and say, here, this is where it stopped. The universe doesn't die the way a star dies, collapsing under its own gravity or exploding in a supernova. It doesn't vanish. It doesn't cease to exist. It just continues, forever, in a state from which nothing new emerges. And here's what we've been avoiding saying directly for the past 10 chapters, what all the data and all the physics and all the inexorable mathematics have been pointing toward. This is not a catastrophe, not in any physical sense, not mechanically, not according to the laws that govern matter and energy and space-time. The universe isn't breaking, it isn't failing, it isn't doing anything wrong. It's doing exactly what the laws of physics require it to do. The terror isn't in the outcome. The terror is in what the outcome reveals about the nature of existence itself. Let's be absolutely clear about what we've learned. Every process we've examined, from the formation of voids to the acceleration of expansion, to the increase of entropy, to the approach of thermodynamic equilibrium, follows known physics, established laws, mathematics we can write down, test in laboratories, verify through observation. Gravity operates according to Einstein's equations. Expansion follows from general relativity. Dark energy behaves consistently with measurements from supernovae, the cosmic microwave background, and large-scale structure surveys. Entropy increases exactly as the second law of thermodynamics predicts. Nothing we've described requires exotic physics, no undiscovered forces, no violations of known principles, no miracles. The universe began in a low entropy state at the Big Bang. Why it began that way remains an open question, but that it did is observationally confirmed. And from that initial condition, every subsequent development follows necessarily from the laws of physics applied consistently across time. Tiny density variations in the early universe were amplified by gravity, not smoothed out. Matter clustered in some regions and evacuated others. Voids expanded, galaxies formed and aged, stars ignited and will eventually die. Black holes will evaporate, entropy will increase until it can increase no further. No intervention required, no external force needed, no design, no intention, no purpose, just laws operating. And here's what makes this particularly important to understand. The outcome isn't punishment. It isn't failure. It isn't the universe running down in the sense of something going wrong with a machine. The universe isn't a machine that breaks. It's a system that evolves according to the constraints imposed by its fundamental physics. And those constraints favor simplicity, they favor uniformity, they favor emptiness. Not because emptiness is somehow better or more natural or preferred by some cosmic aesthetic, but because the mathematics of how energy disperses, how entropy increases, how expansion operates, all drive the system toward maximum entropy states. The second law doesn't have intentions. It's not trying to achieve anything. It's a statistical principle. Given many possible configurations of a system, the overwhelmingly most probable ones are those with high entropy. The universe explores configuration space, and high entropy states vastly outnumber low entropy states. So the universe spends most of its time in high entropy configurations, not by choice, by probability. For most of human history, we assumed the universe was eternal and unchanging. The ancient Greeks believed in a cosmos that had always existed and always would exist in essentially the same form. Medieval scholars inherited this view. Even into the early 20th century, before Hubble's discovery of cosmic expansion, most astronomers assumed the universe was static. Then we learned it was expanding, born in a Big Bang, finite in age, evolving over time, and we assumed, perhaps hoped, that evolution meant progress, that the universe was building towards something, that complexity would increase, that structure would become more elaborate, that the arrow of time pointed toward greater organization, not less. We were wrong about that too. The arrow of time points toward entropy, toward dispersal, toward the dissolution of structure, not its elaboration. And this shouldn't surprise us. We see it everywhere at smaller scales. Ice melts, buildings crumble, mountains erode, stars burn out. Every concentrated form of energy disperses over time unless actively maintained by an external energy source, and even that maintenance increases entropy elsewhere. The second law applies universally. It governs chemical reactions in test tubes and the fate of galaxy clusters across billions of light years. There's no scale at which it stops operating, no exemption for complex systems or living things or consciousness. Organization is temporary. Complexity is an exception, not a rule. Structure persists only as long as energy flows through it, and energy flows always increase entropy. So the universe we see today, rich with galaxies, stars, planets, the patterns of the cosmic web, represents a fleeting moment in cosmic history, a brief window when conditions allow concentrated energy sources, steep gradients, the possibility of interesting transformations. Before this moment, the universe was too hot, too dense, too uniform for interesting structure. Hydrogen and helium plasma filling space, opaque to light, undifferentiated. After this moment, the universe will be too cold, too sparse, too uniform for interesting structure. Individual particles separated by distances larger than galaxy clusters today, moving through a darkness that has no end. The window is narrow, and we exist during it. Not because the universe made the window for us, not because physics ordained this moment as special, but because interesting structure, galaxies, stars, planets, life, consciousness, can only exist during windows like this. We observe this moment because we couldn't exist during any other. Stephen Hawking once noted that the laws of physics don't care about life. They don't care about consciousness. They don't care about meaning or purpose, or whether anything interesting happens. They govern the motion of galaxies the same way they govern the motion of dust particles, indifferently, mechanically, following equations that contain no terms for importance or value. A star forming in a nebula follows the same gravitational physics as a cloud of gas dispersing into emptiness. The formation is not rewarded, the dispersal is not punished. Both are equally lawful, equally permitted, equally inevitable under the right conditions. And this is where the real terror lives, not in the mechanics, not in heat death or entropy or cosmic expansion. Those are just physics playing out, neutral processes, neither good nor bad. The terror is that we attach meaning to things that physics treats as temporary configurations. We look at a galaxy and see beauty, complexity, structure worth preserving. Physics sees a particular arrangement of matter and energy in a low entropy state that will necessarily evolve toward higher entropy given sufficient time. We look at Earth, at life, at consciousness, and see something precious, something that matters, something that should continue. Physics sees complex chemical processes enabled by an energy gradient between the sun and the cosmic background temperature, processes that will cease when that gradient disappears. We exist, we think, we wonder, we ask why, and the universe offers no answer because the question has no physical content. Why implies purpose, and purpose isn't a category in the equations that govern reality. The universe doesn't follow intentions, it follows rules. And the rules produce for a brief time conditions that allow complexity, and then, for vastly longer times, conditions that don't. Freeman Dyson understood this. In his papers on the far future of the universe, he never described heat death as a tragedy. He described it as an inevitability, a consequence, the logical endpoint of processes we can observe and measure. He looked for ways life might persist in that far future, ways intelligence might adapt to ever-decreasing energy availability. But he never pretended the universe cared whether such adaptation was possible. The universe permits certain things, forbids others. and remains indifferent to which possibilities are realized. So this is not a catastrophe in any physical sense. The universe isn't ending, it's not dying, it's not being destroyed. It's simply evolving toward thermodynamic equilibrium, following the laws that have governed it since the beginning. No violence required, no collapse, no explosion, just the patient, inexorable operation of gravity, expansion and entropy across timescales that dwarf human comprehension. Every galaxy that has formed will fade, every star that has ignited will cool, every structure that has emerged from the cosmic web will dissolve back into uniformity, not through catastrophe, through completion. The process is finishing, the reactions running to equilibrium, the transformations exhausting all available gradients, and the universe continuing, empty, silent, still, not dead. Death implies something that was alive, just existing in a state from which nothing further can emerge. This is what the laws of physics produce when given enough time. But here's the question that remains. If this outcome is inevitable, if the universe trends toward emptiness through ordinary lawful processes, if complexity and structure are temporary exceptions in a cosmos that favors simplicity, what does that make this moment? This narrow window when galaxies shine, when stars form, when planets orbit, when life emerges, when consciousness arises to contemplate its own existence. If we're just a brief fluctuation before the return to equilibrium, does that make us meaningless, irrelevant, a cosmic accident of no significance? Or does it make this moment, this unlikely, improbable, impossible moment of structure and complexity and thought, more precious precisely because it's rare? The physics can't answer that. The mechanics don't care, the mathematics remain indifferent, but we care. We're here, we exist, we think, we wonder, and perhaps that's where the meaning actually lives. We began with a measurement, a simple, precise, disturbing measurement that astronomers don't often share with the public, not because it's uncertain or debated, but because once you hear it, it changes the way you see everything. Most of reality is nothing, not metaphor, not poetry, measurable, mappable, verifiable nothing. One hydrogen atom per cubic meter, voids occupying more than 90% of space, galaxies as rare exceptions in an ocean of absence. And we asked why. Why is the universe structured this way? Why does matter cluster in thin filaments while emptiness dominates? Why do galaxies exist at all if the cosmos favors voids? Now, after following the physics across 13.8 billion years of cosmic history, after tracing the mechanisms from the Big Bang through galaxy formation, through stellar evolution, through entropy and expansion, to the final thermodynamic state, we have our answer. The universe is empty because physics naturally favors emptiness. Not through intention, not through design, through mathematics, through the operation of gravity, expansion, entropy, forces that sort matter into concentrated nodes and evacuate the space between them. Forces that create structure temporarily, but trend toward uniformity permanently. We are not looking at a universe that failed to fill itself. We're looking at a universe behaving exactly as the laws of physics require, and that realization changes everything. Picture the entire history of the universe as a single year. The Big Bang happens on January 1st. The cosmic microwave background, that moment when light first traveled freely through space, forms just minutes into January 1st. The first stars ignite in the first week of January. Galaxies assemble through January and February, swelling and merging as structure takes hold. The Milky Way forms in mid-March. The Sun ignites in early September. Earth solidifies a few days later. Life emerges in late September. Dinosaurs appear on Christmas Day. Humans, anatomically modern humans, appear around 11:48 p.m. on December 31st. All of recorded human history occupies the last few seconds of the year. Now, extend that calendar. If the past 13.8 billion years is 1 year, then the era when stars can still form, when galaxies still shine, and the universe still contains concentrated energy sources, doesn't last just a few years. It lasts another 7,000 years on this scale. The universe stays bright, structured, and active for a span so long that our entire first year feels like the opening page of a book that goes on and on. After that, darkness, silence, the slow fade into thermodynamic equilibrium spanning timeframes that make those first years seem instantaneous. Billions and trillions and googles of years where nothing happens, where no stars form, where no light shines, where entropy has finished its work and the universe exists in a state from which nothing new emerges. We exist in the first year, in the loud moment, the brief window when the universe contains structure, complexity, energy gradients, steep enough to drive interesting processes, not by design, by necessity, because observers, beings capable of asking why the universe is the way it is, can only exist during windows like this, only when stars shine to warm planets, only when complexity can persist, only when the universe is far from equilibrium. We couldn't exist during the first moments after the Big Bang, too hot, too dense, too chaotic for atoms to form, let alone molecules, cells, brains. We can't exist in the far future, too cold, too sparse, too close to equilibrium for gradients to sustain metabolic processes, information processing, thought. The window is narrow, and we're in it. Carl Sagan once said we are a way for the cosmos to know itself, and he was right, but not in the reassuring way that phrase is often interpreted. We're not special in the sense of being chosen or intended or designed. We're special in the sense of being statistically improbable. Think about what had to align for you to exist. The universe had to begin in a low entropy state. Why it began that way remains mysterious, but without that initial condition, no structure could form. Tiny variations in density had to appear in the early universe, 1 part in 100,000. Deviations so small they should have been negligible. Gravity had to amplify those variations rather than smooth them out. Matter had to cluster into galaxies. Stars had to form from collapsing gas clouds. At least one of those stars had to be the right type, not too massive, not too small, to burn steadily for billions of years. Planets had to coalesce from the leftover disk of material. At least one planet had to orbit at the right distance from that star, had to have liquid water, had to develop an atmosphere, had to remain geologically active. Chemistry had to explore configuration, space for billions of years until self-replicating molecules emerged. Evolution had to operate across billions of generations, driven by variation and selection, building complexity layer by layer. And all of this had to happen during the narrow window when the universe contains energy gradients, when stars still burn, when matter hasn't dispersed into equilibrium. You are the product of 13.8 billion years of the universe doing physics, not aiming for you, not trying to create consciousness, just following laws, gravity gathering matter, stars forming and dying, planets accumulating, chemistry combining, evolution iterating, and somehow, against overwhelming odds, in a universe that is mostly empty, mostly dark, mostly trending towards stillness, complexity emerged that can look back at the process and understand it. That's not comforting in a cosmic sense. The universe didn't make you on purpose, but it's staggering in every other sense. The terrifying part is not that the universe is empty. We've established that. The data is clear. Most of space contains essentially nothing. The cosmic web is dominated by voids. Galaxies are rare. Structure is temporary. Entropy increases. The final state is equilibrium. The terrifying part is not even that complexity ends, that stars burn out, that black holes evaporate, that the universe approaches thermodynamic stillness. Physics guarantees those outcomes. They're as certain as tomorrow's sunrise, just operating on longer timescales. The terrifying part, the part that genuinely unsettles once you grasp it, is that this moment is rare, and we are here to witness it. You exist during the only epoch when existence is interesting, when the universe is structured enough to create galaxies, stars, planets, chemistry complex enough to support life, brains complex enough to contemplate existence itself. Before this epoch, the universe was too simple. After this epoch, it will be too uniform. This window, this cosmically brief flash when structure persists, when energy flows, when questions can be asked, is all there is. And you're in it, right now, looking out at a night sky filled with stars that won't always be there, living on a planet warmed by a sun that will eventually cool, thinking thoughts that require energy gradients the far future cannot provide. The universe doesn't care. It's not celebrating this moment. It's not mourning what comes after. It's just doing physics, following rules, operating according to laws that favor simplicity over complexity, uniformity over structure, silence over sound. But you care. You look up at stars and wonder. You ask questions about origins and endings. You seek patterns. You build models. You trace the mathematics from the Big Bang to heat death and realize where you fit in that story. And that caring, that capacity to find the universe meaningful despite its indifference, that exists only here, only now, only during this brief loud moment before the silence. The meaning doesn't come from the universe. It comes from you, from consciousness, from the rare, improbable, temporary complexity that can look at 13.8 billion years of cosmic history and understand it. Physics created the conditions. You create the meaning. Remember that stadium from the beginning? The enormous space with just 3 grains of sand scattered across it, illustrating how sparse matter actually is. We are standing in one of those grains, not metaphorically, literally. We exist in a rare pocket of matter in an overwhelmingly empty cosmos, on a planet orbiting a star in a galaxy containing billions of other stars, floating in a universe where galaxies themselves occupy less than 100 millionth of the total volume. And we're looking out at the other grains, the other galaxies, the other rare concentrations of matter, and asking why there's so much space between them. The answer is that emptiness is the default. Structure is the exception. We exist in an exception, and we're asking about the rule. But here's what makes this moment extraordinary. The universe could have been different. If the early variations in density had been slightly larger, matter would have collapsed too quickly into black holes. If they'd been slightly smaller, galaxies would never have formed. If physical constants were tuned differently, the strength of gravity, the mass of the electron, the rate of cosmic expansion, chemistry might not support complexity. We don't know why the universe has the particular laws and constants it does. That remains one of physics' deepest questions. But we know the result, a universe that began in a low entropy state, that expanded rather than collapsed, that formed stars rather than remaining featureless, that created, for a narrow window of time measured in billions of years, conditions where matter can organize into galaxies, planets, cells, brains, thoughts, conditions where you can exist, not forever, not even for a meaningful fraction of cosmic time, but for now, for this rare, improbable, impossible moment. The silence will come, the voids will expand, the stars will fade, entropy will finish its work, and the universe will approach the stillness that physics has been driving toward since the beginning. But not yet. Right now, in this moment, on this planet, during this brief epoch when the universe is rich with structure and light, you are here, aware, thinking, wondering, existing in the only loud moment the cosmos will ever have. And that's not terrifying, that's extraordinary. And perhaps that's why we look up at night, not to understand the mechanics of fusion or calculate the distance to distant galaxies, but to feel connected to something larger than ourselves, to stand beneath stars that won't always be there and know, really know, that we're part of this. A child born tonight will open their eyes to a universe 13.8 billion years old. They'll learn to walk on a planet 4.5 billion years into its existence. They'll ask their first question during a moment that will never come again. And somewhere in that ordinary miracle, in the fact that awareness emerged at all, that matter organized itself into eyes that can see stars, minds that can trace their own origins, there's something that doesn't need the universe's permission to matter. We are the universe looking at itself for a brief, unrepeatable moment. And we've chosen to wonder rather than simply exist, to ask why rather than accept silence, to find meaning in a cosmos that offers none and call that meaning real because we feel it. The emptiness was here before us. It will remain long after. But right now, in this fragile instant between the Big Bang and heat death, the silence has been interrupted. By us, by you, witnessing the only loud moment there will ever be.